Most machine learning performance gains historically came not from more sophisticated models, but from better features. Even in the deep learning era, where representation learning has automated much of the process, feature engineering and feature selection still quietly determine whether a system works robustly in the real world. If you understand how to shape input representations and how to decide which signals matter, you control a large portion of the model's eventual behavior. At the most basic level, a feature is any measurable property or attribute of the data that you feed into a model. In tabular problems, features might be columns like age, income, or transaction amount. In text systems, features might be tokens, embeddings, or linguistic indicators. In vision, raw pixels are technically features, but in classical pipelines they were often transformed into edges, textures, or key points. Feature engineering is the process of transforming raw data into representations that make the learning problem easier. Feature selection is the process of choosing which of those representations to keep. It is important to separate these two concepts mentally. Feature engineering creates candidate signals. Feature selection decides which signals are worth keeping. In practice, they are deeply intertwined, but they solve different problems. To understand why features matter so much, consider the perspective of a learning algorithm. Most models are not magically intelligent, they are function approximators. They can only learn patterns that are visible in the representation they receive. If important structure is buried or distorted in the raw data, the model must work much harder to discover it. In many cases, especially with limited data, it simply will not. A classic example comes from linear models. Suppose you want to model a nonlinear relationship using linear regression. If you feed only the raw input variable, the model will fail. But if you engineer polynomial features such as squared or cubic terms, the same linear model can represent complex nonlinear behavior. Nothing about the model changed, the representation did. This illustrates a key principle: feature engineering reshapes the geometry of the problem. It can turn a hard learning problem into an easy one or vice versa. Even modern deep neural networks, which learn internal representations automatically, benefit from thoughtful input design, especially in structured data domains. Let's walk through the feature engineering pipeline conceptually. It usually begins with raw data ingestion. Raw data is rarely clean or directly usable. Missing values, inconsistent formats, outliers, and noise are common. The first stage is often data cleaning and normalization. While not always labeled as feature engineering, this step directly affects feature quality. Handling missing values is one of the earliest decisions. You might impute with a mean, median, or a learned model. You might add a binary indicator showing whether a value is missing. Each choice injects assumptions into the model. In high-stakes systems, the way missingness is encoded can significantly influence downstream behavior. Normalization and scaling are also critical. Many models, especially those relying on gradient descent, are sensitive to feature scale. If one feature ranges from 0 to 1 and another ranges from 0 to a million, the optimization landscape becomes poorly conditioned. Standardization, min-max scaling, and robust scaling are common techniques to bring features into comparable ranges. Categorical encoding is another major component of feature engineering. Machine learning models typically operate on numerical inputs, so categorical variables must be transformed. The simplest method is one-hot encoding, where each category becomes a binary indicator. This works well when the number of categories is small, but it becomes problematic when cardinality is high. High cardinality categorical features introduce sparsity and dimensional explosion. In such cases, alternatives like target encoding, hashing tricks, or learned embeddings become useful. Each method has trade-offs. Target encoding can leak label information if not carefully regularized. Hashing can introduce collisions. Learned embeddings require sufficient data to train effectively. Temporal feature engineering deserves special attention. When data has time structure, naive models often perform poorly because they ignore ordering, seasonality, and recency effects. Engineers often create features such as rolling averages, time since last event, day of week indicators, or lagged variables. These transformations expose temporal structure that the model can exploit. Aggregation features are extremely powerful in many real-world systems. For example, in fraud detection, individual transactions may look normal, but aggregated behavior over time reveals anomalies. Features like counts, sums, ratios, and moving statistics often provide more predictive signal than raw events alone. Interaction features capture relationships between variables. A single feature might have weak predictive power, but the interaction between two features can be highly informative. Polynomial feature expansion, cross features, and learned feature crosses are ways to expose these relationships. However, uncontrolled interaction expansion can quickly explode dimensionality and lead to overfitting. Text feature engineering historically involved heavy manual work such as bag of words, TF-IDF weighting, engrams, and linguistic features. Modern deep learning has automated much of this through embeddings and transformers, but even today, pre-processing choices like tokenization, normalization, and truncation length significantly affect performance. In computer vision, classical pipelines used handcrafted features such as SIFT, HOG, and edge detectors. Deep convolutional networks largely replaced manual vision features by learning hierarchical representations directly from pixels. However, even in deep vision systems, choices like image resizing, cropping, color normalization, and augmentation remain forms of feature engineering. Now let's shift to feature selection, which addresses a different but equally important question: given many candidate features, which ones should we keep? More features are not always better. Irrelevant or noisy features can harm generalization, increase computational cost, and make models harder to interpret. One of the simplest selection methods is filter-based selection. These methods evaluate each feature independently using statistical criteria such as correlation with the target, mutual information, or variance thresholds. They are fast and model agnostic but ignore feature interactions. Wrapper methods evaluate subsets of features by actually training models and measuring performance. Techniques like recursive feature elimination fall into this category. They often produce better feature sets but are computationally expensive because they require repeated model training. Embedded methods perform feature selection as part of model training. L1 regularization is a classic example because it drives many coefficients exactly to zero, effectively selecting features. Tree-based models also perform implicit feature selection by choosing splits based on information gain. A critical concept in feature selection is multicollinearity. When features are highly correlated with each other, they provide redundant information. Some models handle this gracefully, but others become unstable. Feature selection or dimensionality reduction can improve robustness in such cases. Dimensionality reduction techniques such as principal component analysis occupy an interesting middle ground between feature engineering and selection. Instead of choosing existing features, they create new composite features that capture most of the variance in the data. This can improve conditioning and reduce noise, but it may also reduce interpretability. In modern deep learning pipelines, explicit feature engineering is often less visible because neural networks learn hierarchical representations automatically. However, this does not mean feature thinking has disappeared. It has shifted earlier in the pipeline into data design, pre-processing, and architecture choice. For tabular data especially, manual feature engineering still frequently outperforms purely end-to-end deep learning approaches. Structured data often contains domain-specific signals that benefit from human insight. Experienced practitioners know that thoughtful aggregation, encoding, and transformation can dramatically outperform brute force modeling. There is also an important interaction between feature engineering and data leakage. Leakage occurs when features inadvertently contain information that would not be available at prediction time. This can produce deceptively high validation performance that collapses in production. Time-aware feature construction and careful validation splits are essential safeguards. Another subtle issue is feature drift in production systems. Features that are predictive during training may change distribution over time. Monitoring feature statistics and retraining pipelines is therefore critical in deployed systems. Feature engineering is not a one-time task, it is part of an ongoing data lifecycle. From a systems perspective, Feature pipelines must be reproducible and consistent between training and inference. Feature stores and transformation graphs have become important infrastructure components in modern ML platforms. A model is only as reliable as the feature pipeline that feeds it. As models scale, representation learning increasingly absorbs some of the traditional feature engineering burden. However, the core principle remains: models learn from the signals we expose to them. Whether those signals are handcrafted or learned, the quality, stability, and relevance of features remains central to performance. The most important mindset for a technical audience is to view feature engineering as shaping the information geometry presented to the learner. Feature selection then becomes the discipline of managing signal-to-noise ratio under computational and statistical constraints. Together they determine how efficiently a model can extract useful patterns from data. Even in the age of massive pre-trained models, practitioners who understand features deeply continue to have a decisive advantage, because the bottleneck in many real-world systems is not model capacity but representation quality.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.